Hello, so we are in Lab 8, Conservation of Momentum, and the concept of conservation of momentum is a kind of easy idea, but when you are going to the problem solving, it might be a little tricky. So in this video, I'll go over with a couple of question solving and giving you some tips to solve the conservation of momentum problems. So the first question on your pre-lab is about two friends that are practicing hockey, right? So let's read the problem. So it says Blake and Drew are at hockey practice. Blake's mass is given and the velocity is given. And then they skate toward Drew. He is skating towards Drew, and Drew's mass and velocities are given, which is cool. So we have all the information to calculate momentum for each person. And then they collide inelastically, sticking together. So they collide and then stick together. All right. Now it's asking us to determine the final velocity of Drew and Blake as they slide across the frictionless ice surface. Okay, cool. So we have all the conditions there. It's frictionless, so we don't need to worry about whether the energy is losing or not. And we have given with all the masses and velocities. All right. So here, basically, a collision is happening, right? So when you're applying conservation of momentum, we need to understand where the collision happened and what does it mean by just before the collision and just after the collision. So there are three regions that we need to understand. So we need to understand where the collisions happen, and then what is before the collision conditions and what are the after the collision conditions. So before the collision, so Blake and Drew are traveling towards each other, right? So the Blake's mass is 60 kilogram and the velocity is 10 meters per second. So let's say towards right is the positive direction. So the velocity is positive 10 meters per second. Drew is traveling towards Blake and his mass is 65 kilograms and velocity is -6 because we considered that the towards right is positive direction. So Drew is moving towards Blake, that's to the left. So the velocity is -6. So this negative is really important. You know, velocity is a vector, right? So vector does have direction involved in there. All right. So after the collision, what happens? So the Blake and Drew going to stick together, right? So they are sticking together. So they're becoming to a one system, right? So the system, here we are talking about a system which include two pieces, Blake and Drew. Now in the system, they are sticking together. So the total mass of the system going to be the addition of two masses of two people, right? So it will be 60 plus 65 kilograms. So it's basically 125 kilograms. And the velocity, we don't know. That's what we're going to find it out, right? Okay, so let's say velocity is towards right. We don't know. So if we end up getting a positive value for the velocity, that means these two friends are moving to the right. If we get negative velocity, that means they are moving towards left, right? All right, so the conservation of momentum means that the momentum is stay as the same, right? Before the collision and after the collision. So basically we need to find out what's the momentum before the collision in the system. So as I mentioned here, the system means Blake and Drew. So let's calculate the momentum of the system before the collision. So we need to calculate the momentum of Blake. That's his mass times his velocity. So I denoted it by symbols, mass of Blake times velocity of Blake, plus the momentum of Drew. That's mass of Drew times the velocity of Drew, right? Then let's substitute the numbers. So here it's 60 times 10 because Blake's mass is 60 and the velocity is 10. So 60 times 10. Then I need to add the momentum of Drew, which is 65 times -6. So you may do your calculations. So 60 times 10 is 600, 65 times -6 is -390. So basically you are subtracting 390 from 600. So I end up getting 210 kilograms meters per second. I'm using a calculator here, so I can make mistakes. So please do your calculations by yourself. All right, now we have the total momentum of the system before the collision. Now I need to find the momentum after the collision. Then after that, I can apply the conservation of momentum. All right, so let's go ahead and calculate the momentum after the collision. All right, so now the system is a little different. Now two people are sticking together, right? So the total mass of the system going to be mass of Blake plus mass of Drew. So you add the two masses, time it by the speed of the system. Actually, I have D over here, which should not be, because it should be V of the system, right? Now let's add these two masses and multiply it by the system velocity. So it will be 125 times the velocity of the system. Again, please ignore this letter D. It is not indicating Drew. It's my mistake. I apologize for that. So it should be just V, because we are talking about the velocity of the system of Blake and Drew, right? All right, now conservation of momentum says the total momentum of the system before the collision is equal to the total momentum of the system after the collision, right? So these two numbers, 210 is equal to 125 times the velocity of the system, right? So you may solve for the unknown velocity. So it will be basically 210 divided by 125. So I get 1.68 meters per second, which is a positive number, right? So basically, after they collide, they are moving towards right with 1.68 meters per second speed, right? So the velocity will be positive 1.68 meters per second. Okay, so I basically solved this problem for you, but please do it by yourself, do your calculations. As I mentioned, my numbers may be different. All right, now let's move on to the second question. So here, a 150 kilogram astronaut found himself stand a few meters from the spacecraft. So he's at rest, right? So he's not moving, but he wanted to travel towards the spacecraft, right? So thinking fast, she throws an 18 kilogram toolkit away from the ship at 2 meters per second. Find the resulting speed of the astronaut. Okay, so we need to understand where the collision happened. There's no collision here, right? It's kind of an explosion, because this astronaut is throwing something away from herself, right? So it's a kind of an explosion. So its pieces are separating from each other, right? So let's say it is an explosion, but momentum, conservation of momentum is valid for any collision or an explosion, right? So here, let's understand what is the before the collision scenario and what's the after the collision. So here, before the collision, the astronaut and the toolkit are at stationary. So we can understand this is before the explosion, right? Then after the explosion, the astronaut should be moving with the speed, and the toolkit. Actually, I throw a tool over here. It's easy for me to draft it. So anyway, so he throw the tool. Let's say it's traveling with the 82 meters per second. All right. So can we calculate the momentum before the collision? Actually, here explosion, right? So astronaut and the toolkit are at rest. So the momentum should be 0, right? Because there's no velocity in there. Mass is there, but there's no velocity. So the mass times velocity will be 0. Now, after the collision, what's the momentum? So we know that toolkit is traveling with 2 meters per second. And then when you throw something this way, the astronaut should be moving to the opposite direction. I guess so, but you don't need to think like that. You may think that the astronaut also moving in the same direction. So if you pick the wrong direction, you will end up getting negative values in your answers. That way you can flip the direction, right? So anyway, I am going to assume that the astronaut is moving towards the spacecraft and the toolkit was thrown in the opposite direction to the spacecraft. All right, so now we know that the tool is 18 kilograms and the velocity is 2 meters per second. So we can calculate the momentum of this tool. And also we can think about like how to calculate the momentum of the astronaut. So the astronaut was 115 kilograms initially, right? Now he thrown a 18 kilogram tool away. So his mass will be 115 minus 18 kilograms. And the velocity, we don't know. We're going to solve for it, right? All right, so let's find the, let's apply conservation of momentum. So here, initial momentum is 0. So that should equal to the momentum after the explosion. So after the explosion, I do have two pieces. One is astronaut. So astronaut's mass is 115 minus 18. I need to time it by the astronaut speed. I mean the velocity. That's unknown. That's what we are solving for. Plus the momentum of the tool. So it will be 18 times 2. Remember your units. It's mass, kilograms, and the velocity measured in meters per second. So it will be kilograms meters per second, right? Then you have to solve for the astronaut's velocity. So basically you multiply these two numbers, 18 times 2, 36. And when you're taking it to the other side, it will be negative 36. And you need to divide it by this 115 minus 18. So you will end up getting negative number, right? So you can solve for that number using a calculator. Now the astronaut speed is negative value, right? So negative whatever the number that you get. So as I mentioned over here, this velocity of the toolkit is positive 2 meters per second. So I get the astronaut velocity to be negative number. So it's in the opposite direction to the motion of the tool. So basically the astronaut is traveling towards the spacecraft, right? So here the velocity of the spacecraft is whatever the number you get there, and it is negative. That means it's towards the spacecraft. So our choices are fine. We are good here with our argument about the velocity. All right. Then in the third question, you were given with a bunch of pictures, and you need to find which one is conserving its momentum, right? So if you read the question, you see in all these cases, the gray ball was initially at rest and the white ball was moving along the dotted line from left to right. So here, these pictures are representing what happened to the balls after the collision. So initially, white ball is traveling towards the stationary gray ball along this dotted line. So for all these 4 scenarios, the initial momentum will be about the same thing, right? So you can find the initial momentum of the system for all the 4 systems. It's going to be only in horizontal direction. I don't know a number, but conceptually, I can assume or I can argue that there should be only a horizontal momentum in the systems, right? So there's a momentum towards horizontal direction, towards right for all these scenarios, right? So if the systems are conserving the momentums, their final momentum also should only be in the horizontal direction towards right. Okay, because initial momentum is towards right horizontally along the dotted line, right? So if the momentum is conserved, then the final momentum also should stay in the same direction, right? Okay, so let's try arguing with one of these problems. I'm going to solve for question A, and you may think about others by yourself. So let's think about this one, question A over here. In this A scenario, what is happening? So you see, like, this is the velocity vector for the gray ball. Also, I can call this as the momentum vector because mass of the 2 balls are the same, right? So let's say this represents the momentum of the gray ball. Now, you know, momentum is a vector. So let's think about the component of this momentum. So there's a horizontal component and also a vertical component, right? So this is the components of the momentum vector that represented by the black arrow. Also, let's try the momentum component of the white ball. So there's a horizontal and a vertical component. Now, if you sum these components, like let's think about the horizontal component. So the gray ball does have a momentum about this much along that way, and the blue ball has a momentum horizontally, sorry, not the blue one, the white one has a momentum going that way. So there's a remaining momentum over here about this much, right? So the system does have a total momentum component going in the horizontal direction about this much. So I'm basically talking about the difference between this horizontal vector and this one. All right. Now let's think about the vertical component. So there's a vertical component of the gray ball that's going downward like this one. Then the white ball does have a component that's going straight upward. And there's a little difference because this arrow is longer than this one. So there's a difference between these two. So which resulting in a little vertical component of momentum here. So if you sum these up, there's a horizontal component and a vertical component. So this is not matching with the initial momentum, because momentum to be conserved, we should only have this horizontal component, but we still have a little bit extra, right? So in this scenario A, the momentum is not conserved. Right? So you may try part B and you may draw these vector momentum vectors and see whether there's a remaining piece that's going vertical direction. And if there's nothing going in vertical direction, that means it does only have a horizontal component of momentum. So the momentum should be conserved. All right. I believe this will help you to answer the lab report questions. If you still have questions, please get help from your TA. Thank you, and I'll see you next week.